Welcome. In this lecture, we are going to discuss about digital PID controller hardware implementation in digitally voltage mode control buck converter and some experimental results. So, in this lecture, we are going to talk about digital PID control using Verilog HDL programming, and this programming part we have already discussed. So, now we are going to implement this digital PID controller in a voltage mode control continuous conduction buck converter. So, if we recall our digital voltage mode control, this we have discussed multiple times. So, what are the practical details that we have considered? So, in this particular hardware prototype, we have considered 1.8 microhenry inductor, then 200 microfarad capacitor, and it is tested at 3.3 input voltage, and output voltage is considered between 1 to 1.1, because we will be showing also reference transient where we are changing voltage from 1 to 1.1, but our nominal voltage is 1 volt, and the switching frequency is 200 kilohertz, and we have considered two discrete load resistance. One is a continuous load resistance, this one, another is a switch. For example, we are talking about the output side of the buck converter. So, here we have a continuous load which we call RC, and there is a switch load which is connected to RSW, and this is connected to Q load that we have discussed in the previous lecture. So, if the Q load is 1, then RSW will come parallel to RC and the effective resistance will be smaller. So, it will make a load step up transient, and if we disconnect RSW, then RC will come into picture, the load resistance will increase, overall load resistance will increase. So, it will make a load step down transient. And in this lecture, we also considered, this we have discussed in the Verilog module when we wanted to write the Verilog module, but before that we have also discussed that ADC converter. So, the proportional gain we have considered inside this controller, Kp to be 1.25, Ki, this is all discrete time integral gain 0.13, and discrete time derivative gain Kd, that is 8. So, we have 8 bit ADC, 10 bit ADC, but we are discarding 1 bit. So, we are representing 9 bit, or it can make it 8 bit, and the DPWM resolution is 9 bit. So, typically ADC resolution should be smaller than DPWM, but with 9 bit ADC we are not getting significant effect of limit cycle. So, there is slight instability is there. So, but one can choose 8 bit, only thing you will lose the resolution. So, one way we can increase the DPWM resolution by increasing clock, but we have the the limitation of the controller clock, which is only 100 megahertz clock is available. Then our voltage feedback gain, because we are stepping down using a resistive divider, and this we have got near about 0.27. So, that is the voltage feedback gain, and the ramp voltage that we are considering, because inside the digital controller we are considering this sawtooth waveform, which is a staircase kind of thing. And for the corresponding Q format, we got the real voltage to be Vm to be roughly, I would say not exactly 2 volt. So, this is a ramp voltage. Now, we have discussed that digital PID controller, this is the implementation, and we have also implemented MATLAB in week 3. So, this is the proportional gain, this is the discrete time integral gain and discrete time derivative gain. And in the Verilog, we said these are the parameter, and for Kp we have used Q 4.6, and that is why Kp is coming to be 1.25, because if you see the integer bit, it is in the 2 to the power 0 location. So, it is 1, and this is in 2 to the power minus 2. So, that means 0.25, and the integral we are getting roughly, this is Q 1.9, we are getting 0.13, and the all bits, this is Q 4.6, the sign bit all cases are 0 because all positive gain, and then rest of the thing, this Kd is approximately equal to 8, okay, that we have discussed. So, these are the proportional, integral and derivative gain, these are all discrete domain digital controller. Now, we have made a load step up transient. So, we are again in this case we are making a load step down. So, that means before this our load resistance was continuous resistance in parallel with RSW, and which was approximately coming to be 0.32 0.32 and here it is only RS RC which is R equal to, that is 13.5. So, that means we are making a load transient of almost, because our RSW is 0.33 and our reference output is 1 volt. So, we are making effectively making a load transient of nearly 3 ampere load step. So, here it is a step down transient, this is a step up transient, and for more detail, if you consider step up transient, then we are getting an undershoot of nearly, that means if you consider this undershoot. So, this is coming to be delta V is coming to be delta V is approximately equal to 180 millivolt, which is large. We can always decrease it by setting the suitable controller gain, and we will be discussing the design case study in the subsequent week. And this settling time is coming to be up to this, and each division is 20 microseconds. So, we are getting 1, 2, 3, 4, 5. So, that means it is settling time is roughly around 100 microsecond, and which is like a 20 cycle, because 5 microsecond is my time period. If we zoom the load step down transient, then we will get this overshoot. This is also approximately 180 millivolt, which is also large. We can reduce it, and we will show in the subsequent case study how can you make it faster when you go to design. And the settling time that we are getting, which is Ts, it is up to this point. So, in this case we are getting equal to 80 microsecond, so which means 16 switching cycle, and we can make it much faster. Now, we are considering reference step transient, and in this case we have set the load resistance at is RC value, which is nothing but 13.5 ohm. So, our load current depending upon the output voltage will be RC. So, for 1 volt nominal voltage, so the nominal load current for this case, that means if you set V0 to be 1 volt, then it will come around 70 to 75 milliampere. But you can see we are making a load step up transient. So, this is step up and step down, and if you go to the zoom version of the step up transient, so this is roughly around, it is not exactly, it is reaching here. So, this voltage is 1.1 volt and this voltage is 1 volt, because this axis is 0.2, this is 0.2 volt per, this is a 0.2 volt, because we are talking about voltage axis in this case, and the current axis, this to this is our 2 ampere, and our ripple is also more or less 2 ampere. So, it is there is slight overshoot, but it is taking somewhat longer time to settle. It is going close fast, I mean within like a 20 microsecond, but there is slight undershoot overshoot with respect to the new reference voltage. So, it is taking somewhat more time to reach to the steady state value. Similarly, if you take the reference step down transient, for all these cases we set load resistance to be RC equal to 13.5 ohm, and it can be shown that this is our 1.1 volt and this is our 1 volt. So, it is taking roughly like 80 settling time, like almost 80 microsecond, and there is a very slight, I mean there is no as such undershoot, and it is coming. So, in summary, we have discussed digital PID controller and that hardware implementation, and we have discussed the PID controller programming in the previous lecture, and we have shown experimental case study of a continuous conduction buck converter using digital voltage mode control. So, we have discussed digital PID controller implementation of digital voltage mode control. So, in the next lecture we will go for mixed signal current mode control, where we will apply digital PI control. Thank you very much.